AI voice agents are being deployed everywhere, and when users talk to an AI, they expect an instant verbal response. To pull this off, the system has to process your voice through a speech-to-text model, generate a reply, and run it through a text-to-speech model, all sequentially, within a few hundred milliseconds. Text data is easy. You send a short string, you get a short string back. Speech data is a heavy, continuous stream of bytes that never stops flowing while the user is talking. If developers force this continuous audio stream through the wrong network protocol, the audio chops up and the entire system lags. Choosing the wrong pipe ruins the user experience before the AI even gets a chance to process a single word. The default way we send data across the internet is HTTP/1.1. It relies on a simple request and response cycle, which works perfectly for loading web pages, but it fails completely for continuous audio. If a client wants a live audio stream, it has to constantly ask the server if it has new data, creating massive overhead with repetitive polling requests. The deeper problem lies in the transport mechanism underneath HTTP, the Transmission Control Protocol, or TCP. TCP guarantees absolute reliability. It insists that every single data packet must be delivered and processed in its exact original sequence. This illustrates a concept called head-of-line blocking. Because TCP requires strict sequence, one dropped packet creates a physical barrier, stopping the entire queue behind it. While missing data is retransmitted, a timer ticks up, the client sits idle, and latency compounds. For a live voice chat, a guarantee of perfect reliability is actually fatal. Speed matters much more than making sure every byte arrives flawlessly. The first alternative is WebSockets. Developers use this primarily to connect a user's browser or mobile app directly to a cloud API. A WebSocket starts with a standard HTTP request, but then the connection is upgraded and kept permanently open. This illustrates full-duplex communication. The client and server push data through this bidirectional pipe simultaneously, without requesting permission. However, WebSockets still operate on TCP. If a packet drops, you will briefly pause the data flow to recover it. The engineering trade-off is that you gain universal compatibility across almost all platforms, but you have to manually code the logic to reconnect a user if their mobile network drops out. WebSockets are the most pragmatic standard for passing audio to a third-party API. You accept the minor TCP latency risks in exchange for a simple, flexible implementation. Once that audio data gets past the firewall, the requirements change. This is the internal backend pipeline, where data passes between your proprietary microservices. This pipeline connects backend nodes using gRPC, built on HTTP2. Unlike REST's JSON, gRPC uses protocol buffers, shrinking payloads into dense binary blocks. HTTP version 2 also multiplexes, allowing multiple independent binary streams to travel side by side simultaneously without blocking. You get maximum throughput and very low server load. The cost is that you must define strict, inflexible data schemas ahead of time. Web browsers cannot natively speak gRPC. If you try to use it on the front end, you have to add translation proxies to make it work. Keep gRPC behind the firewall. It exists strictly to connect internal microservices, where you have complete control over both endpoints. For direct browser-to-browser communication and native microphone access, you use WebRTC. WebRTC operates entirely differently because it relies primarily on the User Datagram Protocol, or UDP, instead of TCP. This animation illustrates how UDP avoids head-of-line blocking. It transmits data without requiring receipt acknowledgements. If one packet drops off the line, the remaining packets continue moving at full speed without pausing. A dropped packet just translates to a tiny fraction of a millisecond of static in your headphones, rather than freezing the entire real-time conversation. To get this speed, you take on massive architectural complexity. Bypassing standard firewalls requires you to deploy and maintain complex stun and turn servers, just so the peers can locate each other. Look at this technical diagram. Integrating WebRTC with standard enterprise networks often requires dedicated gateway infrastructure, like a signaling function to translate protocols and a media function to handle ICE and transcoding. WebRTC delivers the absolute lowest audio latency possible, but it demands a brutal upfront investment in dedicated infrastructure to manage the connections. There is no absolute best protocol here. The right choice is dictated entirely by where the data is traveling within your system architecture. This checklist outlines the decision matrix. For live browser voice chat, WebRTC is the mandatory choice. For streaming user audio to a cloud-based API, WebSockets are pragmatic. And for passing data internally between backend microservices, gRPC is required. You accept heavy backend signaling setup with WebRTC for the lowest possible latency. You accept minor TCP latency with WebSockets for universal compatibility and fast implementation. You accept strict protocol buffer schemas with gRPC to get maximum internal data speed. Analyzing the specific path of the audio packet is the only way to allocate engineering resources effectively and build a functional AI voice agent. Check the description below for links to documentation and SDKs.